Hi, I'm Eric, and today I will be talking to you about my work at the University of Ottawa with Dr. Broadbent on the rigidity of monogamy-of-entanglement games. First, I will introduce the game that we studied, which is the quintessential example of a monogamy-of-entanglement game. Then I will discuss the main rigidity results that we show about this game, and finally, give two cryptographic applications of this result. First, the original example of a monogamy-of-entanglement game was introduced by Michel Ferrer-Kanevsky and Wehner in order to study the limitations of quantum tripartite correlations, a property called the monogamy-of-entanglement. We refer to this game as the TFKW game after the initials of the authors who introduced it. The game consists of three players, or three parties, a referee who has fixed actions, Alice, who plays against two players, Bob and Charlie. The referee holds a single qubit quantum register, whereas the players may hold arbitrary registers. The game is played as follows. First, the players agree on a shared state, that is, a quantum state that may have arbitrary entanglement between their registers and the referee's register. Afterwards, however, the players are isolated and may no longer communicate. Next, Alice samples a question, just a single bit, uniformly at random, and informs the players Bob and Charlie. Then, based on her question, Alice makes a measurement on her single qubit register. If the question is 0, then Alice measures on the computational basis. Otherwise, she measures in the Hadamard basis. In order to win, the players try to guess the result of Alice's measurement. They only win if both players correctly guess Alice's measurement result. A strategy for such a game can formally be described by the shared state, as well as their players Bob and Charlie's projective measurements that they make in order to come up with their guess. The important quantification of this is given by the winning probability of the game, simply the probability averaged over the questions that the players win given a certain strategy. It may be expressed in this way. Here we can see the expectation value of the tensor product of the measurement operators, which corresponds to the probability of them all measuring the same outcome. A different way to quantify the value of this game is using the bias, similar to what is studied for non-local games, which is a wholly equivalent quantification. However, it makes for a nice expression it has a nicer expression in terms of the observables of the measurements rather than the projectors. The observables are simply unitary operators that correspond to each of the measurements. And in terms of observables, the bias may be expressed in this way. We will return to this later. The important results shown in the work of Michel Ferrer-Kanevsky and Wehner is to find a bound on the winning probability of this game. And in fact, they found an optimal strategy that has some interesting properties. In order to study this optimal strategy, it's useful to look at Alice's space as represented by the block sphere. Her measurement observables, corresponding to her measurements in the computational and Hadamard basis, may be expressed as follows. In the computational basis, Alice's measurement observable is Pauli Z, and hence her measurement corresponds to the z-axis of the block sphere. Similarly, on the Hadamard basis, her measurement observable is the Pauli X operator, and it corresponds to the x-axis of the block sphere. The optimal winning probability over all strategies for this TFKW game is co-squared pi over 8, about 85%, corresponding to a bias of square root of 2. What is very interesting about this game is that this optimal winning probability is in fact attained, and it is attained by an unentangled strategy, which is a strategy where Bob and Charlie share no entanglement with Alice, and simply make a guess of, simply send a state to Alice, and make a guess of the outcome without holding any entanglement for themselves. This state is the Breidbart state, which sits in between, directly in between the Z and X axes on the block sphere, and hence it sits directly in between the 0 and plus states in the space of one cube. For this strategy, all the players have to do is both guess outcome 0, and in this way they both they win with probability 85% approximately. This is not the only optimal unentangled strategy. There's three other states that sit in between the computational and Hadamard bases on the block sphere, and they can be expressed as follows. These states actually form a pair of mutually unbiased bases, just as the computational and Hadamard bases do, and they can be and when we refer to them as the Wiesner-Breidbart states, and the Wiesner-Breidbart bases as the corresponding base pair of bases. A natural question to ask at this point is whether these are all the possible optimal strategies for this game. And it turns out that in a sense, this is true. This brings us to our main result, which is a rigidity result on the optimal strategies, or rather, on the optimal strategies of the TFKW game. And what we have is that an optimal strategy of the TFKW, the state of an optimal strategy of the TFKW game, is not necessarily a Wiesner-Breidbart state, but it is necessarily a convex combination of these four states. In this context, a convex combination is a superposition of the Wiesner-Breidbart states, where, a superposition of terms where the term on Alice's space is a Wiesner-Breidbart state, and the term on Bob and Charlie's spaces are simultaneously distinguishable, which means that both Bob and Charlie can make a measurement and distinguish which term of the superposition they have found themselves on. This is equivalent to saying that the states have orthogonal support, the terms have orthogonal support on both Bob and Charlie's spaces. Also, in order to win optimally, the players must measure in the same basis on the two questions in order to make their guess. That is, the basis that the measurement that they make is simply to make the measurement that distinguishes which term of the convex combination they're on, and then make they make the proper guess based on the Wiesner-Breidbart state strategy that they find themselves on. In order to prove this result, we adapt techniques used for proving rigidity of non-local games. First, the first step is to study the non-commutative game polynomial of the game. That is a polynomial with non-commutative variables, whose expectation value with respect to the state gives the bias. The polynomial is expressed as follows. This is the same expression as the bias of the state, just expanded explicitly in terms of the observables of the TFKW game. An important thing to note with this game polynomial is that for any strategy corresponding to a representation of the polynomial, we have that square root of 2, the bias, minus the game polynomial must be a positive operator. In fact, also, if the state is optimal, the expectation value of this operator, square root of 2 minus b, must also be 0. One way to characterize positivity of operators is by expressing them as the sum of squares. And this TFKW game polynomial has a simple sum of squares decomposition given as follows. What we note is that since each of the terms of the sum of squares decomposition is positive, this expression square root of 2 minus p must be positive. And also, if the expectation value of this on a state is 0, each of the terms must act as 0 on the state. This gives a family of relations on the operators of an optimal strategy. In particular, that Bob's operators for the two questions and Charlie's operators for the two questions must commute with respect to the state. This this relation can be used to construct a representation of an abelian group from the state using the Gauss-Hatami to construct a representation of an abelian group from the operators using the Gauss-Hatami theorem. This representation, since it may be able to, it is able to decompose as a direct sum of irreducible representations, induces a decomposition of Bob and Charlie's spaces, which in turn induces a decomposition of the state. This decomposition is exactly the decomposition as a convex combination of simultaneously distinguishable terms, which is used to show the result. In order to be useful in applications, this result can be extended to show more properties of this rigidity. First, we show robustness, which is to extend the rigidity result to non-optimal strategies. This is if a strategy wins epsilon close to optimally, then it must be, we show that it's necessarily possible to dilate Bob and Charlie's spaces such that the state of the strategy is on the order square root of epsilon away from the state of an optimal strategy in norm. Also, we show rigidity for parallel repetition. That is, if Alice plays n games in parallel with Bob and Charlie, and they win each one optimally, then the state of their strategy must be not a convex combination of Wiesner Breidbart states, but convex combination of n-fold tensor products of different Wiesner Breidbart states, which takes this form. We also have robust rigidity for the parallel repeated game, which again takes a similar form. If each each qubit, the game at each qubit wins with near optimal probability, then the state of the strategy up to local dilations is near the state of an optimal strategy. Here we note that we have these the order is optimal or nearly optimal. However, we have these coefficients which can in general be large. Finally, in order to make this more amenable to applications, we want Alice to be able to conclude rigidity from the winning statistics of a family of games played in parallel. So we're able to show using similar techniques to those used by Reichert, Unger, and Manzoni to show rigidity used by Reichert, Unger, and Manzoni in their work on the rigidity of the CHSH game. We were able to show that if the players win the correct proportion of many games played in parallel, then for a large fraction of the games, they must win them near optimal. Now we can use this result to to get some applications of cryptography. The first application is a weak string erasure scheme. Weak string erasure is a cryptographic primitive introduced by Koenig, Werner, and Rohrschläger, which can be used to construct both bit commitment and a Boolean transfer. Ideally, this acts as a black box that produces on one side a string x and on the other side a string x hat and a set of indices iota. The weak string erasure is said to be correct if both x and the indices iota are uniformly random, and the string x hat matches x on iota. In the real world, the weak string erasure is not undertaken by some black box, but by an interaction between two players, Alice and Bob, who do not trust each other. This means that the correctness has to be modified and supplemented in order to have this be a secure object. First, the correctness can only hold if Alice and Bob are honest. Next, if Alice is honest, she wants security. So she wants to make sure that outside of the string where their bits should, the substring where the bits should match, Alice would like to be assured that Bob has little information about the bits there. This is quantified via a min entropy. On the other hand, if Bob is honest, he wants to make sure that Alice is unable to guess which bits he knows. That is, she's unable to guess iota. In this, this is quantified by the registers, the state being in tensor product on those registers. Koenig, Werner, and Rohrschläger show this. Give a construction of this in the noisy quantum storage model. We will construct weak string erasure in a three-party model inspired by Monogamy-of-Entanglement games. Here, Bob has an additional sidekick, Charlie, who collaborates with him. However, he is isolated from Bob. On the other hand, Alice cannot communicate separately to Bob and Charlie. She can only communicate by broadcasting publicly. Finally, in order to achieve security, Alice would like to have the same security against Charlie as she has against Bob. That is, that Charlie is also unable to get much information about the remaining substring. Classically, this is no different from the standard two-party model of Alice and Bob communicating with no additional assumptions, and hence bit commitment, and therefore weak string erasure cannot exist. However, quantumly, this is different, as we can construct a functioning weak string erasure protocol that's based on the Monogamy-of-Entanglement, the TFKW Monogamy-of-Entanglement game. The protocol proceeds as follows. First, Bob and Charlie prepare a random state encoding a string y in some reasonable Breidbart basis phi. Afterwards, they are isolated, both knowing which state that is. Next, Alice chooses a subset of the indices. She measures that subset in a random reasonable Breidbart basis, giving some substring. On the remaining indices, she plays the TFKW game with Bob and Charlie. She verifies that they win the right proportion of the time, and therefore she can therefore it follows using rigidity that they have prepared a convex combination of reasonable Breidbart states. Finally, Alice outputs the string that she measured on the set of indices J. Bob outputs the string that he prepared on that set of indices, and outputs the set of indices where his preparation bases and Alice's measurement bases matched. Here, the security for Alice is given by the rigidity of the MOE game, and the security for Bob is because the rigidity is not in fact that rigid. Since Bob is not constrained to prepare a particular reasonable vertical state, and Alice does not learn which reasonable vertical state he prepares, he is able to still prepare a random string that Alice, of which Alice does not know the bits if the bits that she measures in the wrong basis. For the second application, we studied randomness expansion. Simply, randomness expansion is a procedure that can take a short, uniformly random seed and produce more fresh randomness from the seed. This has been studied in various models. In particular, it's been studied. Randomness expansion schemes have been constructed based on verification of entanglement using the CHSH game and particular computational assumptions, in particular the learning with errors assumption, which implies noisy trapdoor clocking functions. We use, again, an MOE-based model to construct a randomness expansion protocol. Here, this model consists of a verifier, Alice, who is able to make quantum measurements. However, her measurement settings are able to be are always publicly shared. Also, there are two provers, Bob and Charlie, who are untrusted, but they are isolated from one another, and they are polynomial time computers. Our protocol for randomness expansion proceeds as follows. First, the provers prepare some shared state between themselves as well as Alice, but after that they are isolated. Next, Alice uses a pseudorandom generator to get a long question string data, as well as a set of indices of that string. On all but that small number of indices, Alice plays the TFKW game with Bob and Charlie, which she uses to verify the rigidity, and therefore to learn something about the shared state. In particular, what she learns is that since the state is a convex combination of Wiesner Breidbart states, it's in particular a convex combination of terms that are in the XZ plane of the block sphere. Finally, what she does is that she measures the remaining bits in the basis I minus I, which, since it's mutually unbiased from any basis in the XZ plane, gives near uniform randomness. Here, we have randomness expansion without the need to verify entanglement, and also without the need to have particular computational assumptions. We can use the very general assumption of one-way function, which imply pseudorandom generators. In conclusion, we give an example of rigidity beyond the usual domain of non-local games. Also, we show that this has applications, in particular to bit commitment and randomness expansion and new tripartite models. There are open questions. First, some of the coefficients that show up in the proofs are rather large, and it would be helpful for applications if those were able to be improved. Also, more generally, are there other applications of this result? And even more generally, what other similar games, either monogamy-of-entanglement games or more generally extended non-local games, are similarly rigid? Finally, I'd like to thank some of our collaborators, Arthur Mehta and Sebastian Lloyd, as well as NSERC for funding. Thank you.